Before we begin today, just one housekeeping order. We ask that you place your questions in the Q&A box at the bottom of the screen. We will address all questions at the end of today's presentation. We will also be videotaping this webinar this afternoon, and we will make sure that each of you get a copy of the presentation once this event has concluded. So with that said, we'd like to get started. So our agenda for today is quick market update, followed by battery chemistries, cell selection process, engineering considerations, transportation and safety, about Excel, and then Q&A. So the market update, we want to give you a quick overview of the market update. We know that all of you have been experiencing shortages with the supply chain. What's really driving that, and I think we all know, is the EV market. Tesla puts between 5,000 to 7,000 cylindrical cells in each of their battery packs, and those sales are increasing. Panasonic, LG, they're all supporting Tesla. So therefore, there's small commitments that are left over for other customers. Additionally, we see additional EV and ESS batteries from cylindrical cells that are really pushing that production into the EV market. And then there was COVID. Obviously, COVID impacted the production on some of the top tier manufacturers, including LG, Murata, Panasonic, and Moly. So moving into this year, and obviously last year with the impacts of COVID, there was limited investment in the cylindrical cell production. As we all know, there's a long-term road to get capacity up and moving, and there's also some shortages in the raw materials. This is not going to wane, and based on the industry experts that we coordinate with, we're looking at another 2, possibly 3 years until which time they can catch up. The top-tier battery manufacturers can catch up with the capacity and actually increase production. So what does that mean? That means that the 18650s remain as a shortage. There is more opportunities for 21700 cells. Main expectations and main expansions are really in with the Chinese, the Korean, and the Japanese companies. But as Tesla moves forward and starts to move into more of the 21700 cells, it will free up some availability. So I'd like to now turn that over. Oh, one more slide. Sorry, there's worldwide battery sales by chemistry. Just a brief slide to give you an update as to where we are. I think everyone knows lithium ion is the leader in terms of the growth. We do see a little bit of nickel metal hydride growing, as well as nickel cadmium. But again, lithium ion takes the lead in terms of applications for the rechargeable market. I'd like to turn it over now to Bob Fay.
Hey, everybody. I just want to talk about battery chemistries a bit, talk about the different rechargeable batteries as well as go a little deeper into lithium chemistries. The first and probably the oldest long-lasting or the oldest original rechargeable battery would be the lead acid. It's been around for well over 100 years and very, very common. It's out there everywhere. Every car that's not an EV car contains one of these things, and they're used in many large-scale battery banks. They're very common, like I said, high power density, durable, and a wide temperature range, but they're very large, very heavy, and they're still very useful where size and weight is not an issue. Next, please. NiCad, that's another older traditional rechargeable battery chemistry. It's at end of life these days. It has a lot of memory effect issues with it, as well as containing cadmium, which is a toxic metal that's not good for landfills. But they're very common still, high power density, good low temperature performance, and they're very good for handheld devices. And nickel metal hydride basically came out to replace NiCad. They're also very common. They have an advantage over lithium because they don't have the transportation restrictions, but they do have a high discharge rate, and they are more expensive than NiCads. And last, of course, is lithium ion, which is basically taken over the world. They have very high energy density compared to NiCad, very limited memory effect. long life, low maintenance, but they are high cost, and there is concerns about safety, of course. Um, as a result, there's a lot of transportation restrictions in shipping lithium ion batteries, but they are taking over. They're becoming very common with almost every electronic device. They're being used in EV cars, of course. So that's where the future is for rechargeable. Just want to go over some slides showing a comparison between the different um, main chemistries we talked about. Most of these numbers are very general and they're not necessarily specific to a certain brand because you look at different data sheets and they tell you different numbers. But comparison voltage, lithium ion will have 3.6 volts versus 2 for lead acid and 1.2 for niken and nickel hydride. So you'd sell and energy. Go ahead. Sorry. Energy density, of course, lithium ion outshines all the others by quite a bit, over twice as high energy density as the nickel-based chemistries. Next, specific power. Well, this is where nickel hydride really outshines. So the power per weight is much better with nickel hydride, but lithium ion still does very well in this regard compared to lead and niken. Cycle life, lithium ions again outshine the others. 1,000, we're even seeing cells with 2,000 cycles out there available these days. Charge time, well, lead acid is much slower than the others. Lithium ion tends to be much faster as far as charging, shorter charge times versus lead acid. And self-discharge rate, again, lithium ion outshines the others. Nickel hydride, where the big drawback is the very, very high self-drain rate, which is like 30% per month. Then we have costs. Well, lithium ion, because of their energy density, is doing very well in this regard. And this chart just shows the different main lithium chemistries. There are several out there, and these are generally the 5 most common ones available, but there are improvements and changes being made all the time. But first of all, the lithium titanium oxide is one of the newer chemistries. It has improved output, better charging time, better lifespan, durability, and maybe a greater operating temperature range than the others. This becoming more popular in automotive. Lithium iron phosphate is becoming very popular because of the high safety compared to cobalt manganese systems. And the voltage is a bit lower, 3.2 volts, but these are very common with places where we worry about safety, such as aviation products, hybrid systems. The Sedgway personal transporter uses lithium iron phosphate. Then we have lithium cobalt oxide, which is the original lithium ion chemistry, probably the most widespread out there, very broad use. It's being used in a lot of laptops, has high specific energy, but it doesn't have as good safety as the other chemistries. And then we have lithium nickel manganese cobalt oxide and lithium nickel cobalt aluminum oxides, which are becoming very popular with electric vehicles. And Excell Battery works with a lot of different cell suppliers. We consider ourselves cell agnostic. We don't tie ourselves into any one particular cell manufacturer. And a big reason for this is due to what Michelle explained earlier, where there is starting to be a shortage and high demand for cells. So we have to make sure we have different cell suppliers to work with. We work with all the major cell suppliers around the world, including what you see on this slide. At this point, I'd like to turn it over to my colleague Ron, who will talk about cell selection.